Well, why don't we get into the harmonics theory first?
So
and
this,
I think we're going to have lots of conversations about this, Ray. So no rush. So we got a lot to cover.
The important thing there was I started from that one, and these ratios are all calculated off 586.24 million years to give all those figures. So they do fit pretty well with all the Dewey stuff. They fit pretty well with my stuff. They fit well with the astronomical stuff. They fit well with everything, really.
So this is your sort of anchor number right here?
That one there, yeah. Yep.
And through harmonics, you're able to derive all these other numbers.
Yeah. Now, at this stage, there's no reason why there should be 11 and 5 and 13 and 5 and 7. It's just that's observed what's there.
Mm-hmm.
So when we want to get to the reason for it, I said, okay, I don't know what the longest cycle for the universe is, but, we need to go to this first, don't we? We haven't done this one yet, have we?
No, we haven't done this one yet.
Okay, so my theory was, this was in the 1970s, remember? And at that time, if people haven't seen the Mandelbrot set, they should look at the Mandelbrot set and a couple other things. People were starting to look at nonlinear systems. Before that, you couldn't do these things by hand. They were too complicated. But the Mandelbrot set was based on the idea of a very simple equation, and you keep feeding something back in over and over and over. And it develops this fantastic 3D dimensional looking thing. And if people haven't seen it, they should look at it. I haven't got one here. So I decided this is based on nonlinear systems, and I decided, in fact, my first talk at the Cycles Foundation, hang on, let's find that one. Oh, that's that same one we're on, yeah. Mm-hmm. Okay. I gave a talk at the Foundation for Study Cycles in 1989, and I called it Towards a Unified Theory of Cycles. It was the sort of first shot at it. Mm-hmm. And at that stage, I presented this diagram and the moon's orbital parameters affect atmospheric tides on Earth. The planets affect the sun. We talked about that a little bit. And the sun has many effects on the Earth, and the Earth has many effects on the economy and all these other things there. And this is not intended to be an accurate thing. It's just supposed to show there are lots and lots of things affecting lots of other things that cascade from astronomy through to weather systems and other stuff like that, and eventually through to the economy. So that was the sort of picture I had in my mind. But one thing I found, and which I read that Dewey had also found, and it went ding at that point, he said, we find the same cycles on Earth and on the sun, and they generally got the same phase. And in fact, he said sometimes the Earth ones show up slightly sooner than the sun, which indicates that they're not coming from the sun. And so I began to realize that the pattern I was finding of harmonically related cycles weren't operating on this system, but were operating on a system of nonlinear equations. And so when you have a nonlinear equation, I don't know if I've got that graph in here. No, I haven't, I'm sorry. What happens is, let's supposing the sun is affecting something on Earth, the rainfall, which is affecting the wheat growth, say. And let's say the sun's got an 11-year cycle, which it has, and that affects either rainfall or temperature in some region, and those things affect the growth of wheat. Then would we expect an 11-year cycle in wheat? We might, and you might find that in some places, but and in fact you do in England, because it's colder climate. But in America, you grow wheat in a zone that's about the right temperature and rainfall. So what happens is, I'm going to draw a graph with my arms here. You've got to remember that. And as we go across there, the bottom there, we're changing the temperature or the rainfall, and up the side is is how much wheat gets grown as a result. And it looks like that. So as we go from left to right and back again, the production of wheat goes up and down and then up and down again. So for one cycle of the sun affecting rainfall or wheat or whatever, we get 2 cycles of wheat, and we end up with a 5.5 year cycle, which in fact there is.
Mm-hmm.
So that was giving me, that was the theory behind all of this and the harmonics. So then I said, okay, let's supposing that each one thing is affecting another by making, I came to the conclusion it's all just waves in the universe. I joked about that at my first talk in the 1980s, but very soon after I decided, yes, this is right. So we've got this is frequency. So we, in cycles, we usually work in periods because that's the way we think. Frequency is just upside down periods, right? Just the opposite, divide them into one. If we start with a frequency of 1, it doesn't matter what. It might be one period of 14 billion years, I thought it was at this stage. And we have one wave that oscillates that very slowly over that period. It's going to make other waves that oscillate twice, 3 times, 4 times, 5 times, 6 times, and so on, all the way up in that same time. And remember, my axiom was the universe consists of a wave that develops harmonics. So there they all are. And each of these does the same. So the number 2 wave also develops harmonics, 4, 6, 8, 10, 12, 14, 16 frequency. And 3 makes 6, 9, 12, and 4 makes 8 and 12. But I put 2 in there, and there's a reason for that, is that 4 got made in 2 ways. We had 1 went to 4, but 2 made a 4 as well. So 4 is stronger than 3 or 5. And so when we add those down and get 2, and so the things we feed back in from the side here are these totals coming out the bottom. And so it goes on. And when we get to 12, we see that gets made in a lot of ways. So the 12th harmonic is a very important one, very powerful one. So we can do that. So first of all, I did this by hand, and I did it up to 100 by hand.
So let's go back for a second, Ray, just to
sure.
make sure, like, let's talk about this 12th harmonic.
Yeah.
Okay.
Yeah, so the 12th
so
harmonic.
You're saying, you've got 1 times 12.
Yeah.
You've got 2 times 6 here, right?
Yeah.
You've got 3 times 4 here.
And 4 times 3, but 4 is already 2 ways. Yeah.
And 4 times 3,
which is also 4 times 3 and 2 times 3, 2 times 3, right?
2 times 2 times 3.
Yeah.
Okay.
And you get 6 times 2, but 6 had 3 ways of being made. 6, 2 times 3, and 3 times 2. So altogether, there are 8 ways of getting there, 8 paths from 1 to 12.
So essentially, you start with 1 wave, right? And it breaks into 2 waves and then 3 waves. And those waves can interact 8 different ways to form the 12th harmonic.
Yeah, so I'll just correct you there, not breaks into, but creates. So the number 1 wave is still there all the time. Right. It's just gradually losing energy to these harmonics over long, vast periods of time.
I mean, essentially, this all takes place on a guitar string also, right?
No. Guitar strings have harmonics, but you only get that first line because a guitar string is one-dimensional, and you pluck it, and it makes the harmonics, but they don't each do the same. You have to get in 2 or 3 dimensions, and I did some studies on that, and I did some simulations, and I found that yes, in 3 dimensions, harmonics will develop. In 1 dimension, they don't.
Okay.
So it's, and the best way I can explain that is that in 3 dimensions, a wave, if the fabric of space is getting this done to it, it's doing it in 3 directions at once. So when you get the 3 effects, when the 3 come together, it's not linear. It's having a non-linear effect. It's stronger than that, and that's why they happen. Now, I don't think these higher order harmonics start happening here until the universe has been going for a long time. It's initially just doing that first line, and gradually the other ones come in. I've got a diagram that shows the flow of energy like that, and we'll get to that at some point, I think.
Okay, but bottom line is, this is how you've constructed and identified the strongest harmonics.
Yeah, so this is all the harmonics, but we're interested in the strongest ones. So this is the same calculation I just showed there, how many ways each harmonic gets produced. So
there are, if we look at 72, for example, that has about 70
something
5 different waves
are being made. Yeah, yeah.
And 96 has about 110,
112 or something.
112 different ways of being made.
Yes.
So these are the strongest harmonics up to about 100.
Yeah. So that part I did by hand. Then I started using computers. But there's a little more to come out of this. Those are all going up. The number of ways are being made are much greater. But when you pluck a guitar string, it does make the 96th harmonic, but it's incredibly weak. It's the we have to look at the diminishing power as we go to higher harmonics. When you pluck a guitar string, the first, second, third harmonics are quite strong, and then it's gradually dying off. So you're getting an opposite effect. And when you incorporate that, which I've done in this one, we'll see that we get, I've done here, how many ways each harmonic is produced divided by the harmonic number, which is an attempt to say they get weaker as you go to higher harmonics. In actual fact, the harmonics theory works if it's the combinations divided by the harmonics, or if it's divided by the harmonic squared, or any power of the harmonics. The results are identical for all of those in terms of that it works. So in this case, we can see now that the strong ones here are 48, 60, 72, 96. If we divide those by 12, we get 4, 5, 6, 8, which was the original ones I found in the New Zealand economy. So this is looking promising. It's showing something like that's going on. And in fact, there's some more other ones there. I wonder what those are. And it turns out those ones are the notes of the scale. So I've done do, re, mi, fa, sol, la, ti, do. And I've got mi flat and T flat, which if we're in C, is E flat and B flat. And that's exactly what I found in the wheat prices originally. Lots of those ones interacting. Now,
okay, so just gonna stop again, right? And kind of revisit and make sure it's clear what we've done here. So we've taken this idea of a wave.
Yeah.
And then, the wave becoming 2 waves, or not becoming, but how do you describe it?
Producing the other waves, yeah.
Producing the other waves.
It's a non-linearity of that wave that causes.
I mean, are these essentially kind of, what is it when 2 waves interact, right?
Yeah, no, they're not really interacting. Let me mention, I didn't describe, I can describe non-linearity a little better. When you have waves in the deep sea, they're effectively more or less linear, but as they get near the shore, the speed of the waves varies with the depth. And so the deeper it is, the faster they travel. So what happens is the peak of the wave starts overtaking the trough. So the wave goes from like that, it starts becoming and it breaks. So that sort of thing is going on with the waves. And when you analyze a wave that's breaking, you'll see that it's got lots of harmonics present in it. So that's the process that's going on. It's the one wave that's changing shape that's causing all these harmonics to be present. And after enough time, those waves become strong enough to be present in their own right, not just as parts of the feature of the other wave.
And those waves, produce these harmonics.
Yeah.
And these harmonics have ratios to each other. So,
yeah,
the ratio of 72 to 48 is, this is
3 over 2.
3 over 2. Or 1.5.
You can see Dewey's ones here. You can see 12, 24, 48, 96 times 2. If we take 24 times 3, we get 72. If we divide it by 3, we get 8, which is that one left of the 12 there. So the strong waves give other strong waves when you multiply by 2 or 3 and divide by 2 or 3.
And this also gives rise to the musical scale. Yeah.
So this is giving you a picture which is very like what Dewey had, and it gives you music. So it's yeah. And you can see why I call it harmonics theory.
Yes.
Now that previous one was done with all ratios of all numbers up to 100. I then got the computer out and I said, let's calculate that up to 1,000,000. So I did that. And what happened is, I think there's a version of this. Let me just see if I can find it.
So
it's not. I haven't got all my graphs here. I'm missing some important ones. Okay, we'll go back to where we were. You can cut that piece out.
Okay.
Not there yet. Okay, I've got a version of this, which I haven't got here, sorry, which has, we link up the ones that are ratio 2. So we go 2, 4, 8, 16, 32,
Right,
and you see it's making an arc going downwards, right?
Let me just, so this is the same, you did this, we did this up to 100, right?
Yeah.
On the previous chart. And so now you use the computer and you did it out
up to a million.
To a million.
Yeah. Now,
so there's got to be more ways to make, 144, let's say, than there is to make 12, right?
Yeah.
So why are these?
Because I divided it by divided by the harmonic number, so that like I did in this one here, right? So this is not that graph, it's this graph.
Right. So this is count of harmonics, C of H divided by H.
Yeah.
Divided by the harmonic. So just explain, do that for, say, one of them. So how does that, for 12, for example?
Well, 12,
that had 8, right?
That's got about a 1.2 there, hasn't it? So that should.
So it's 12 divided by 8.
Yeah, that's what it looks like, doesn't it? Yep.
Okay.
On that one. Yeah.
Got it.
Yeah. Now, can you draw a line from 2 to 4 to 8 to 16 to 32?
Sure. 2 to 4 to 8.
So the peaks of the things.
Yep. To 16.
Yep. And to 32.
And to 32. Okay.
And if you can see 64 there. Okay. Now you can see that's sort of like a curve going up and down.
Is here.
Yeah. Yeah.
Yep.
Now do another one that goes through 3, 6, 12, 24, 48, and 144.
Sorry, let me just start over. It was not too neat. All right. 3, 6, 12,
24,
24,
48.
48.
Oh, yep. 144. Oh, am I right? Yeah, that's right. 288. No, sorry. Knock that last one out. Knock that previous one out. Sorry, I started going wrong. So we go 48 to 96. We're going up in doubles, aren't we? I started multiplying by 3. 96 to 192 to 384. Go to 768 as well if you want.
Okay.
Okay. Now that's one of Dewey's lines, and then there's another. Now we can go to 9, which is not very big.
Okay. There's 9.
And 9 and come up to 18.
Okay.
And 36 and 72 and 144.
Okay.
And 288. 576 and 1152. Now you can see what's happening here, can't you? Each time we put a factor of 3 in, we've moved along to the right a bit, or moved up a bit, or whatever you want to call it. And so these I call these families of harmonics, and I've got a graph that shows all of these. And then so what happened there is we went times 2 times 2. Then if we want to go to the strong ones, we had to put a times 3 in to get to 12. 24, 48 going times 2, and then a 3 again to 144. Now, an interesting thing happens here. When we get to 288, we've got to do a times 5 to get to 1440.
Okay, so now we're talking about these strongest ones. So 12 to 20. Yeah. Well, let me just clear all these. So 12 to 24 is times 2. 12 to 48 is times 2. 48 to 144 is a 3.
Yeah, that's right.
And then you got a times 2 here.
And then a times 5.
And then a times 5 to get to the next peak. Times 2.
Yeah. And then times 3 again till I get to 8640. And times 2, times 2, times 2. And then you get, no, knock that last one out. It's a times 7 to get from that one. Well, you get a times 7 after that anyway.
Times 7 here.
Yeah. All right. So you get that's the pattern. So you can see why in another table I want to just
This is a 3.
Well, you can do it from
right?
Either 34 or 560 will give you times 7 to that one, or 69, 120 give times 7 to the other one. And it's a
Right.
matter
And
of
then
taste
this is
which ones you
a
do.
5 here or a 7? This was a
That's a 5.
5.
Yep. Yep. You might as well put the first 2, 2, 3 in as well. The beginning.
From right.
1 to 2. You get 2 and 2 and 3. That's a 3.
Sorry, can't draw there. Just fix that one. All right. So this is a 3.
Yep. And a couple of 2s before that.
2 and 2. So this is a 2.
Yeah.
And this is a 2. Okay.
Yeah. So the whole thing goes 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, 2, 2, 7. So you can see that although it's mostly 2s and 3s like Dewey had, you do need a 5 and a 7 occasionally to get the really strong ones. And you can, and that table I had there that had those groups of cycles, a 7 and a 5 in there, but they also had some other numbers in going further.
This is a 7 here? 69, 1.
Yeah, there's a 7 there. Yep. Yep.
Okay. All right. So this was all produced by Harmonics Theory.
By that one simple calculation, just
by
following
that one
now,
simple calculation, and it produces the structure
yeah,
that explains the cycles that Dewey found.
Yeah.
And the ratios of the cycles that Dewey found.
Yes. Yeah. And so all the ones he finds are not just those top ones. There are some of these other fairly strong ones, but not those ones way down the bottom there, right?
Okay.
Now the next step I did, you can move that now. Yeah, that was up to
a million,
right?
Right.
10 to the 6. I did to 10 to the 10, 10 to 20, 10 to 30. Each time a new model of PCs came out with a faster processor, I went a bit further. This was the last one I did. I went up to 10 to the 50 something, right? It fades out at the end.
Down here?
Yeah.
Okay.
Yeah. So ignore the stuff past about 10 to the 50 or so, because you can see it starts to go wrong. Now, there's two things that are happening. One is there's this wavy envelope at the top, which we were looking at there. It carries on with waves along the way.
Kind of goes like this.
Yeah. Yeah. But also, there's a big block of just a mass of what would be past any test for white noise of all those, that big black blob, right?
Down here.
There. Yes. Now, note that the first one goes from 0 up to 1.2. The second one goes from 0.8 to 1.16. The next one goes from 0.82 to 1.1. So they have, in fact, got a huge, big blob of black stuff below there as well. Now, in a lot of theories, and the Russians were very interested in this, they said, so is this 1 upon F noise? I said, well, it can be 1 upon F to any power, but it can be 1 upon F.
What was that? What are you talking about?
They talk about 1 upon F noise.
1 upon F?
Yeah, the frequency.
Okay.
1. And a lot of systems have 1 upon F noise they can detect. And in some of the theories, some of the physics theories, they have this whole background radiation, which is 1 upon F radiation. Or in harmonics theory, it can be 1 upon F to some power. It doesn't matter. It doesn't care what the power is. But sticking out above those, so the vast majority of the energy ends up in this noise, right? But always there are some that stick up, and that's a log scale. They stick up a long way above that are the ones that we observe, right? And in fact, all the structure of the universe is only the bit that sticks above. They have this problem of missing mass. This explains the missing mass. The missing mass are all these ones that you can't detect individually because there's so many of them. They're too close to each other. So so then I started to look at, okay, what's happening with that whole thing up there?
Go back one slide, Ray. When you say this whole thing up there, are you talking? Oops.
Yeah, this whole thing. You take basically that's 3 rows end to end, right? So what I've done is I've taken the envelope along the top of that.
This structure up here.
Yeah, that's right.
Okay.
Across all of them. And so what I've done is originally, remember we did 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, 2, 2, 3, 2, 7. We got that far, right? I've taken this way up there And eventually you do get 11, a 13, and a 17, and eventually a 19 as well.
Okay.
And all
Go
those
back
things
one slide.
Yeah.
Go back one slide.
Yeah.
So this is,
the
this
shape
is
of the top
1
of
to
that.
10 to the 18th. And then
Yep.
this is 10 to the 18th to 10 to the 36th. And
Correct.
this is 10 to the 36th to 10 to the 54. And you did these as each new processor came out.
Yeah. Yeah, that's
and
right.
then
Well,
essentially you're taking the peaks, if you
Yep.
read, this is like reading a book, left to right, left to right, left to right.
Yeah.
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 And then we get to the next chart. And so what you've done then is kind of take the peaks like we did on the
Yeah.
previous chart,
The biggest peaks.
up to 100 or a million, whatever it was.
Yeah. So
And
I call them the main line.
And you've
So
established the
main line means,
ratios between successive peaks.
yeah, and I call that the main line of harmonics. Now they are very important ones, very strong ones, but there are other ones in between them that are also important as well. That's not quite as important. And there's a couple of things that come out of this. One is you see all the ratios of 2 and 3, like Dewey had, and you see the other factors coming in as well from time to time.
So you got a 5 here, you got a 7 here.
7 there, yeah.
You got an 11
and you'll notice,
and a 13.
Yeah. You'll notice that every time there's a 5, there's a peak after it comes here. And there's another 5, and then we come to another peak, number 1, number 2, number 3. So there's one ratio of 5 between each of those peaks.
And a peak, and then 5 and a peak.
Yeah, there's another 5 before that. You missed out peak number 3. It's not such a big one.
Okay, so that corresponds to that peak.
Yes.
This 5 to this peak.
Yep.
This 5 to this peak.
Yeah. No, to the next one.
No 5 here.
That one. No, don't count that little one. That second one.
Okay, you think it goes to this peak?
Too close to the other one, yeah.
All
well,
right.
You can put more in if you want. There's another peak between 1 and 2 as well. Yeah.
Interesting. Okay.
So when you're doing the ratios of 2 and 3, a ratio of 2 is the most important ratio. Everyone notices ratios of 2 in lots of things, right?
Mm-hmm.
The ratio of 3 is important, but we do notice a ratio of 12. And in fact, humans have used ratio of 12 lines in an inch, 12 inches in a foot, and 12. They've used dozens for all sorts of things. Mm-hmm. And they do occur in nature.
Yep.
So then the next important ratio is 2 to the power of 8 times 3 cubed times 5. So when the 5 comes in, you get a ratio of 34,560. And that was a big peak in this one. Here we go. A big peak there, 34560. On this one's 17280 is about as high.
560 right here.
So you can call that raised number if you want.
And you said that was 2 times
2 to the power of 8.
2 to the power of 8.
Times 3 cubed.
Times 3 cubed.
Times 5.
Times 5. And why is that significant?
That's significant because that's when when you get at that ratio, you get that big peak number 1. And near powers of that number, you get these other big peaks.
So are you saying that there's 8 2s in here and 3 3s?
Yep. And 1 5.
Up to the first peak here. Sorry.
That's right. Yeah.
Sorry to keep slowing you down, Ray. I know
That's
this
okay.
is
now the others won't all have the same number of 2s and 3s.
So you're saying to this first peak here.
Yeah.
We've got 1 2
1
3,
more 2.
4,
1 more
5
2.
6 7 8. So let's say here. Okay, and then we've got 1 2 3 3s and 1 5. So if you multiply all these together, you get that 34,560.
That's correct. Yeah.
And we're calling that raised number. Why?
Yeah. Well, I came up with it first.
Okay.
Well, people probably had the number before me, but it's important in the universe because although these other peaks aren't exactly that ratio apart, they are typically that ratio apart, right?
Okay. Yeah.
And it was clear to me that if we looked at the size of the observable universe, which is the Hubble scale, which is about 13 or 14 billion light years, if we repeatedly divide that by raised number, we get, I haven't called it that before, 3, 4, 5, 6, 7. We get, the first division gives us the typical spacing of galaxies. The next division gives us the typical spacing of stars. The next division gives us the typical spacing of planets. The next division gives us the typical spacing of moons. The next two divisions don't give anything obvious, even though they're in the human scale. They're about 1 mile and 2 inches. The next division gives you the typical spacing of cells. The next one gives you the typical spacing of atoms.
All right, and you have this plotted out on a chart, right?
I do, yeah. Do you want me to try and find it? And the next one gives you the typical spacing of nucleons. I think. No, we'll have to race through to find it. Here we go.
There it is.
Yeah, that's the one which has got it. So that's showing my impression of the scales that are observable in the universe, but I tried to do it independently of what I know about the harmonics theory, but I can't because it's in my mind. But they are the things that have names, and people have studied these, and they have found regularities in the spacing of galaxies and the spacing of planets. And the spacing of atoms, very much. We have bond lengths, right? And nucleons have very definite spacings. So these things do have regular spacings that, like, there's a wave nature. Supergalactic clusters, there's a wave nature to those as well. That's quite a fascinating one, which we'll get to at some point. But there are other associated ones. So although stars have a spacing, and when the galaxies, ARP and TIFT and a few others have done stuff that show these spacings of galaxies. With planets, you had, what's the fellow that had his law for the planetary spacings? His name won't come to my mind. But no one had done it for stars. So I got Norton's Star Atlas out, which I had. This is a long time ago. And I put all the nearby stars in, and I did 3D calculation. And I looked I did the comparative spacing between every pair of stars in there. And when I did that, it gave a bunch of peaks, which were all very close to Dewey's common cycle periods. And you got the 9.6 for the links, and you get 8.88, you get 4.44, and you get 5.9, you get 11.86. You get all these ones which are connected with these cycles. And so, and the one, I then did a program that tried to look for a grid. I thought, is there a grid of these things and arranged it like a crystal, you know? And so I ran that on the nearby stars, and it gave that there is a grid, and the spacing is 4.43 light years. Very close to Dewey's 4.44 years. So when people say the stars do influence our lives, they're right, but not in the way they think. These waves that are through the stars are pulsating through us all the time. And they're all there. Yeah.
All right, good. So let's stop sharing for a minute, and let's just
stop sharing.
Have a chat.
Yep.
And we've put people through a lot.
Yeah, that's a lot. Yeah.
That's a lot. And we're going to continue the conversation, but I just want to kind of summarize for people what you've covered so far. Yeah, and make sure I understand it, right? So you started doing cycles research independently, as in high school, basically.
Yeah.
And then went to college and ended up doing some work for an insurance company, discovered these cycles in New Zealand economic data with ratios, of 4, 5, 6, and 8.
Yeah.
And then you discovered Dewey's work.
Yeah.
Independently.
What's his name? The guy, Lane, came and gave a talk in New Zealand, and I got invited to that by my broker. And he mentioned this foundation research. I said, hold that one a moment. I'm going there.
And so then you actually came to the United States to spend time at the Foundation for the Study of Cycles. And this was after Dewey had already passed away, right? And
yes.
Who was running the foundation at that time?
Horowitz,
right?
Yeah.
Horowitz, who made all those beautiful red books.
Yes, that's right. Yeah, that's a wonderful thing he did, isn't it? That's his legacy.
Very nice. That is his legacy.
Yeah.
So then you discovered Dewey's work, and the work of some Russians as well.
Yeah, that was later. That was in the 90s. Yeah.
And you make a master catalog of all the cycles that Dewey found, as well as cycles observed in climate and in geology.
Yeah, I probably missed out that I used to go into the university library, and I would go to all different sections, and I'd just look for anything to do with cycles. So I'd go to geology, I'd go to climate, I'd go to astronomy, I'd go to atomic structures. I go to everything, and I'd look up everything to do with cycles. And so I would spend days in a row going there and taking notes.
And now you have this catalog of cycles.
And now it's not as comprehensive as Dewey.
The structure that explains all these cycles and produces all these cycles. And that's how you stumbled, or you came up with harmonics theory.
Yes.
And miraculously, your harmonics theory does explain all the structure that you saw, the relationships between the cycles that you cataloged from anywhere you could find.
Yep.
And how did you come to suspect that harmonics theory explained those ratios? I mean, I know you saw that first instance of, in your first cycle study, right? You had the 4.4 and the 5.9 and the...
So there were musical ratios.
Right.
In the 70s, it's worth mentioning also, there was a lot of interest in nonlinear systems.
Mm-hmm.
So that was clear that had something to do with it. Mm-hmm. And I knew that nonlinear systems would make harmonics in a nonlinear system. I should mention that my curious mind had studied other things independently of this. Mm-hmm. I'd studied what is the nature of the basis of the ratios of the notes in music, Mm-hmm. And at that stage, they tell you the equitempered scale, and that doesn't really quite do it, but it almost does it. Mm-hmm. And so then I started looking at the ratios and that, and I worked out for myself what is the correct frequencies of the scale. Then I discovered that was called just intonation, and that would be known for donkey's years. I keep rediscovering things, but the beauty of rediscovering things is when someone else tells that, it's right because you worked it out for yourself. And if you work it out and someone else said it as well, then it's probably right. If you work it out and no one else says it, maybe I made a mistake. I should mention I made a mistake with my original version of the harmonics theory calculation, had a mistake in it. And it took me 2 years to realize that, I suspected it earlier, but the other one was, the correct calculation is harder than the one I did originally. So I had to go back and redo that. And I just came across something the other day where I noticed from notes that I made a mistake in something else, and I corrected it and went on. You're testing it all the time against nature and other people's work. It's important to do that. Yeah.
So if somebody is studying cycles today,
mm-hmm.
right? So we know, for example, we use digital signal processing, Fourier analysis, right, to detect cycles in time series data.
Yes.
How should we use harmonics theory in order to find the strongest cycles?
Yeah.
So let's say just take the stock market, right? So we have the 40 month or the 3.389 years. 3.389 years. Okay.
Yeah. The funny thing about that was Richard Mogi had continued to do, Gertrude Scher had done 40.68, so had Edward Dewey, and he got 40.68. And I said to him, my calculation gives 40.67. And he said, well, that's near enough, I suppose. Anyway, he sent me an email one day, all excited. He said, I've just rerun it, and it says that the period over the whole thing now, it's 40.67. So you have things like that are a lot of fun.
If we take that as kind of the anchor cycle, then we, divide by 2, divide by 3, and look for those.
That's right.
Cycles.
And those other ones, the 4.44 year cycles there as well.
Times
and the
2 and times 3.
Yeah. So I would say that one way of doing it, which I've done at times, is if you've got a set of cycles in anything you're doing, be it a commodity or the stock market or something else altogether, and you find some cycles and they look a lot like some of those ones I've listed there, I would say you could use that period, because if you're trying to optimize something and you have to find the period as well as the phase and amplitude, then it's working harder. If you give it the period that's there and say, let's assume it is that, let's assume they got something right, and we'll just find the phase and the amplitude, then you should get a slightly better result. Because if the period's slightly off, because your period will always be off, you've got finite data. If you're going into the future, if you've got the correct period, it will get more accurate into the future. Yeah.
Okay. Fantastic. Well, Ray, I really appreciate you spending this much time with us. And I think that we've covered a lot of good ground, and that will serve us well as we then continue to unpack this and explore its manifestations in the many different places that you've observed it.
Yes. So next time your first question is, Ray, what's the longest cycle?
And that's 586 million years.
No, that's only the longest one that we've observed.
That's the longest one that we've observed, right?
Yeah.
So yes, we didn't unpack that one here, but I think
I think that's a good one
through enough for
next time
today.
People are fresh.
And we'll spread this out over a couple of weeks, and then we'll continue. You know, you've been working on this for 60 years, Ray,
not quite
or more. And
it is almost, isn't it? Yeah, it is pretty close. Yeah.
And you've amassed an incredible body of work, and I really look forward to sharing more of it with the members of the foundation and beyond.
Yeah.
So thank you so
Thanks,
much.
Richard. And I appreciate the way that you're doing it, which is, make sure we get each thing right. That's very good.
Yeah.
Excellent.
I think that's
I go
really
too
important,
fast otherwise.
because otherwise it just looks kind of like a blur to everyone. But
that's
I think there's something here. I think it's very important for the foundation to pursue it. And I think it can contribute to us ultimately achieving Dewey's goal of establishing a science of cycles.
Yes. Yeah.
And you've got some wonderful quotes from Dewey on that. And maybe we can start with those next time.
Yeah, that's a good one. Start with Dewey and Chizewski quotes there, because those guys both understood a lot of stuff. Yeah. And I love their quotes. They're next time. But because Dewey's quote, it's still true that people still don't incorporate cycles into all these other sciences. Yeah. So he said that in the 60s. Here we are, 55 years later, people are still not doing that.
Yep.
There are forces for ignorance in the world. Yeah. Indeed. Sadly.
All right. Thank you so much, Ray. Have a great day in New Zealand. And
you have a good night.
Look forward to talking again soon.
Yeah. Thanks, Richard. See you.
Bye.